Oh, okay, so we are live. Great. All right, I see that one person has been able to get in. All right, so for today, our goal is to finish up the section on data statistics and probability. We're going to be going over line plots, histograms, probability, combinations, and permutations. So for these two right here, these are still going to be visual representations of data. Excuse me. Now with probability, remember what we talked. What is the main purpose of data is to make predictions. This is where probability comes very much into play. Then we're going to be playing with combinations and permutations. These two are very much like cousins, and we're going to get right into it. Starting off with line plots. So line plots, they're the same information that's on a frequency table, basically just a normal table that shows a distribution of data, and we just put it into a line plot. And I'm going to draw one, and you might have seen this in sports or in other applications. So let's first draw a frequency table, and then a line plot. That way we can make a comparison. Let's make a frequency table. So we're going to be talking about a gym. So here we're going to be looking at weekly gym visits. I believe they're opening up gyms next Friday in Texas. Then here are the number of students using the gym. So we have people that attend the gym 0 times a week, there's 1 student. And for someone who has attended the gym, well, let me just go ahead and finish. So you can attend the gym 0 times a week, once a week, twice a week, 3 times a week, 4 times a week, 5, 6, and finally 7 times a week. And you stop at 7 because the week only contains 7 days. If you find a way to include more than 7 days in a week, please let me know. I'd love to hear that. So then we have how many people that go to the gym once a week? We have 2, and we have 3, and then people who go 3 times a week would be another 3 people. And 0. Just line them up because it's kind of hard to see. 1, 0. Just knowing that these people go together. Okay. So in total, we're only talking about 3, 6, 9, 10, 11. We're talking about 11 students in total, but we want to know their frequency of going to the gym. We can represent the data differently. We can do this. Let's see if I have enough space. I do not have enough space. Go ahead and draw a number line. 7, 6, 5, 4, 3, 2, 1, 0. So this was our frequency table. Now we're going to be talking about a line plot. How many people go to the gym 0 times a week? We have one person. So here we're going to draw a little X on top. We have 2 people. We go 1 week. We have 3 people. Times 3. 4, 0, 5 is 1. It's much easier if we just leave it blank. Just know that this is blank. This means 0 if there's no little X's. And here we're having each X signify one person. And on 6 we have 0, and then 7 we have just one person. So this would be a line plot. So instead of seeing the frequency table, these you could also write it down like this. And to some people, this is much more visual because, again, we're not dealing with numbers per se, we're looking at things visually. Something else that I want to point out is the X's are always going to have to lie on top of the value. We can't really go to the gym 2.5 days a week. You're either at the gym or you're not. So the X's are only going to be on top of each whole number, not in the middle. Otherwise, if you start complicating it, it's just going to be like this big old mess. So we try to keep things simple and be very rational in the ways that we're applying math. Math are just numbers, but the way that we're trying to make it fit into our reality is always the biggest challenge that we face, but once we deal with it, math is able to be our friend. So what we notice here is that there's basically the number of visits are distributed unevenly. It's not like there's an equal number of people that visit the gym on different amounts of different days. So we call this an uneven distribution. If you notice, it's like, right. See? Uneven. So we will know that the highest frequency, or people who go to the gym more often, are going to be people who go more people go to the gym 2 or 3 times a week compared to any other day of the week because we have more people attending that many days a week. We also want to point out from our previous lesson, we were talking about range. What is the scope? So there's 7 days a week, but we're going to include 0 here on our frequency table and also on our line plot because it's possible you don't go to the gym any of the 7 days. It's possible. It's not necessarily very good not to exercise nothing at all, but it is a possibility. And there is one person who does not go to the gym at all. So we need to go ahead and label this. So with the line plot, we have to start from 0 and finish at 0. You can't go to the gym any less. I mean, that'd be breaking the laws of reality. And then you can't go to the gym more than 7 days a week. I might see it on a line where a line extends into infinity, but for our range, we stop it at 0 and we stop it at 7. Something else I want to point out is an outlier. So an outlier is looking at our cluster right here. An outlier is not in the middle of most of the data. So most of the data is concentrated here. There's actually one person who loves to go to the gym every single day. There's someone who likes to go there 5 days out of the week. They're a little unusual, but the person who's the most unusual of all is the person who goes 7 days a week. This person is called an outlier. And with a line plot, it's much easier to notice that very visually. You can take one look at this graphic and know, okay, people who go 7 days a week, they're not in the majority. It might take me a few more seconds to discern that from a frequency table. So whenever you see information presented to you, like in a different kind of graph, table, or chart, you might get different options. It'll be the same data, but they might show you like the information and they want you to calculate something using a frequency table, or they might show you the information as a line plot. So you need to become very comfortable with reading data from different charts. Okay, so we're going to go ahead and do an example with line plots. Go ahead and erase. So we're going to be talking about people who took a driving test. Okay. So let me explain the setup right here. So in grades, you can get an A, which is usually from, depending on what scoring system you have, it's sometimes like 90s to 100, B's, 80s, 70s, 60s, and then anything that's below a 60 would be an F. I know in a lot of countries you don't use like 100 as the maximum on your score. You might use a 10. So this would be like something under 10. Anything that's 9 point, between 9 and 10. 9 and the 8s. Like if you have an 8.1 in the United States, we would just call that an 81. A 7s, 6, and then anything less than a 6 would be an F. So this would be our lowest. So knowing on our number line we go from 0 onwards to larger numbers, F is the lowest score. So we're going to put the F, or the lowest scores, on the left side. So let's say no one failed. Woohoo! And then we know that 3 people passed. So we're just going to, instead of using X's, we can also use little circles. So we say 3 people got D's. Then we say that 1, 2, 3, 4, 5, 6. 6 people got C's. Okay. And then 1, 2, 3, 4, 5. And then 5 people got B's. Okay, and then A's, 2 people got A's. So from this line plot, we can tell that the most common grades were B's and C's, because the most people who got a grade were in the C's range, and then the second place, following visually, was people who got B's. The least common grade that people got was A, and no one got an F. So if we were going to rank by how often, so C was most common. And then we could call A's were very uncommon. We could even call those the outlier. Some of you might argue that F could be considered an outlier, but no one got an F, so no one could count for that. It has to be at least someone who has a grade. It just has to be the least common one. So we know possibilities range from A to F. But our actual data set ranges from A to D because no one got an F. So keep that in mind. If they ever ask for the range, keep in mind, so like range of possibility. Just move some stuff around here. That's it on line plots. One question that you could get on the exam is if it's going to tell you to use a frequency table, so like the table that we had drawn before where we actually use actual numbers, and then ask you to place an element on the line plot. So with the digital, computer-based exams, they might tell you drop a pin where we have the highest frequency. So it might tell you like label C because we know that C is most common, or A would be very uncommon. So take that into consideration. And some of you might be wondering, like, oh, well, why are we going to have that? Why can't it just ask me the between? So let's say we had a multiple choice question, and it would ask you which grade was had the highest frequency. You could just circle C if it was saying that like C was the most common. That's great and all, but with as we're progressing from paper exams into like computer-based exams, it is pretty neat that you might be able to just drop a pin where it is. I remember like when I used to take paper-based exams, instead of being very easy on us and wanting to also test us on our knowledge on line plots, they'd actually draw 4 different line plots, and then I'd have to circle which one of those line plots was the correct one. So I have to analyze like 4 different charts and find out which one was the correct one. If any of you have played those games where you have to spot the differences between 2 pictures that are nearly identical, it becomes very difficult. So this is where technology becomes very helpful. It's able to test you much more directly. So I need to go ahead and plug in this device. Just a moment. Okay, we are plugged in. Right, so that's it for line plots. Next up, we're going to move on to histograms. So histograms, just like line plots, they show frequency. However, they have a very different way of doing it. Some of you might even say, like, well, they might look very close to bar charts. let me go ahead and use a see what's the best way I can go ahead and translate the information. Let me draw one. So unlike bar charts, there's not a space between them. And you're like, well, okay, so some people might want to put spaces between the actual bars, and some people might not. There's actually an important difference between histograms. Let me go ahead and just draw one. All right. Well, with histograms, we're able to see how it changes through time. Always, always, always. With bar charts, you have the flexibility of like swapping like the x and y axis for whatever you want, because histograms show frequencies. The y axis, the one going up and down, the vertical one, that's going to be your frequency. How often? Here on your x-axis, that's going to have to be your group, a label. It doesn't necessarily have to be a number. If it is a number, it might just be like a placeholder, like a zip code. Like how many people go have packages delivered by zip code. The zip code isn't actually a number. It's just a placeholder. So let's say here in this example, we have eye appointments by month. We can go ahead and say that these are different months. So these are different groups. So we could say here that there's most eye appointments are in September. That would be like the most common one. And we could say that, should have been this one just a little shorter. This one is the second most common, and this one could be the third most common. Just to visually organize our data. And we know that the least common, people are going for less. Oh, hi, I see another student who logged in. Is people getting eye appointments in January, so like least common. So let's say I'm the manager of the optometry or optical, and this is the graph of how many people have come in for appointments so far in the year. And I see spikes around the time, like shortly after school starts, a little bit where people are starting to get ready for getting new prescriptions before school, and also a spike around February. So I would more likely want to hire more people or have more staff on hand for these 3 months. Whereas with January, it could be okay to get away with having less staff on hand. Great way of visually seeing information in order to make decisions. So let's say We don't necessarily want to know the frequency of something. We want to look at a histogram also. You have the option. So I'm going to go ahead and erase this example. I'm going to add to the definition. Excuse me, that's just my dog barking at the mail delivery. So with histograms, I can kind of like marry histograms like with pie charts, because remember with pie charts, this represents an entire whole or 100%. Same thing with histograms. I can distribute my data in such a way. I can do this. That all of the data that I lay out here in the histogram, my total, if I add it all up, can be equal to 100%. Now, in the previous example with the number of eye appointments, they can all equal to 100% over 1 year, and then I could convert it into percentages. Or you could just make it easier on yourself, and if you have like a chart software or graphing software, you can go ahead and already put percentages in with it. One of my favorites is like Microsoft Word Smart Art, but there's other software and also free programs that you could use to do this. So we have our percents. So we want to add everything up. We know it's going to be 100%. Let's say that you're working like with decision making, and someone gives you a report, and like you're starting to look at numbers and you see discrepancies. This is where most people get busted for fraud, when their percentages don't match up what numbers correlate to each other. So like, okay, numbers correlating wholes, starting to sound like ratios. Yes, that is correct, because we're going to be playing with that. Right here. So let me go ahead and erase. We're still going to be talking about histograms. Okay, I'm going to go ahead and leave this one for a homework question. That way I can like draw the graph nicely using like computer generated software instead of a very messy picture. What I showed you already though is enough to answer the take home quiz that I'm going to be emailing you later. Great thing with the take home quiz, you can go ahead and watch all the videos again. If I talk too slow for you or too fast for you, you can even on YouTube, you can, where the little gear icon is. You can click it and you can change the video speed. So the speed that normally we're watching is 1 times. I find that if something's too slow, I can watch it at 1.25 times speed, or if something's too fast, I can watch it at 0.75 speed. These are the labels YouTube uses. You can try to do 1.5 speed, 1.75, or 2 times speed. I'm telling you, it's really fast. I'd have to be someone who's talking really, really slow, or someone who's talking really fast when you want to like go with the outliers of speed settings. Just a little tip. Oh, I see another student has logged in. Okay. So now we're going to be talking about probability. I was just talking about that there's going to be a take-home quiz that I'm going to go ahead and email by tomorrow. And you can, with the beauty of the take-home quiz, you can go ahead and watch all the other videos that are in the playlist. And you can even, if you click on the little gear symbol, you can change the speed of the recording. And if you think I talk too slow, you can make it faster by playing at 1.25 speed, or slower by playing it at 0.75 speed. Okay, so now we're going to get into probability. So the types of probability that we have, we're going to be talking about simple probability, independence, and dependent probability, but I'm going to start off with simple because it's simple. So this simple probability tells us the likelihood of something happening or not happening. So the probability can be expressed from 0 to 1. So when you're saying how probable something is, you can express it from 0 to 1. So what's the probability of something? So let's say that this was a coin. It's actually a washer. And I would flip it and ask what side it would fall on. That would be the probability of it falling on itself. Some people would argue that there's a 50-50% chance of it falling on one side compared to the other. I also want to point out that it's possible that it could land on its side. I have seen it where it lands perfectly on its side before, so there's actually a probability of it landing on this side, and then this side. But if you add up all the probabilities together, it's going to add up to 1. Just like with a histogram or with percentages, if we add up all of it together, we end up with 100%. Just that with probability, we're just talking from 0 to 1 instead. Okay. So let's say that there's going to be a random event, and you want to find out what is the likelihood of it happening. This is with probability. That's how it's a very big in decision making. It's kind of like let's say that you want to buy a piece of equipment. You know it's cheaper, but it may not last you as long. So you want to find out, is it worth buying this equipment even though it's cheap? If it's going to break down even before I use it, it's not worth my money. But if it's the probability of it breaking down is very low, then it's worth buying the piece of equipment. So let me go ahead and erase, and let's do an example. Okay. Did any of you ever get to play the game Twister when you were younger? Where there is a big mat on the floor, and there is little different circles with different colors. And if you would spin, I think it was a spinner, it would land on a different color, and then if it was supposed to be a hand or a foot that you needed to put on the different colors, and by the end of the game there might be different people who are tangled up in different weird positions trying to put maybe one hand in one different color and then a foot on a different color. So if we look at that little spinner, or just any spinner, let's go ahead and divide a spinner into different pieces. Yes, I know it looks like a pizza, but we're very comfortable talking about pizza, so that's very great. So this is a little spinner, a little thing that we flick with our fingernails. So here, let's go ahead and number them. 1, 2, 3, 4, 5, 6, 7, and 8. So here we have the spinner, and let's say they have an equal area. We know that there's a 1/8 probability of it falling on each one. And we know that because there's 8 pieces, and for that one piece, it's one possibility of the 8 possibilities. Now, okay, easy enough. Let's find out, like, let's say that you are being competitive and you want it to fall on only a certain numbers. This is very much like people who are trying to play the lottery. So let's say that you want the spinner to land on numbers 4 and 2. What is the possibility of achieving a favorable outcome? So I want it to fall on 2 and 4. Let's go ahead and label this. Alright, so visually we can tell that there's 2 out of 8. Since we want the probability of getting a favorable outcome, the formula we're going to have to use is favorable outcome divided by possible outcomes. So like the possibility of it falling on what we want it to fall on, and then all possibilities. So there are 2 possible favorable outcomes. It can either fall on 2 or it can fall on 4. Those are great. We want it to fall on one of those 2. Now, what are all the possible outcomes? It could fall on 1, 2, 3, or any other of these numbers. So there's 8 different possibilities in total. So this right here, well, let's go ahead and simplify. We can go ahead and simplify this further. 4. That is our probability. We can write it like this. Because it's still with simple probability, we can express the probability as any number from 0 to 1, 1/4 is the same as 0.25. They both mean the same thing. Or I could even express it, if I wanted to, as 25%. This is still acceptable, because 25% of the value of 1 would be 0.25 or 1/4. So all of these are acceptable answer choices right here. I believe I've seen examples where people try to calculate your probability of winning the lottery, of actually like just winning a number, and then it becomes much less likely, like the higher the prize of the lottery is. And I realize this is why I don't buy lottery tickets. It's just very, very, very unlikely for me to win the lottery, because my favorable outcome might only be one possibility, where there could just be way too many possible outcomes where it might not be worth my money to do so. Okay, so let's go ahead and do another example, because this is exciting. So let's say that we keep on playing this game. We just keep on spinning and spinning and spinning. And you spin for a few times, and we just document how many times it falls on different numbers. So the same rule applies. That we want the spinner to land on 4s and 2s, but what's the possibility of having achieved, excuse me, a favorable outcome? So let me go ahead and work this. And this is no longer going to be called simple probability, because simple probability is saying it's more of a what if. Now we're going to move into experimental probability. With experimental probability, you actually go ahead and do it. You actually, so instead of possible outcomes, you're gonna your formula will change from favorable outcomes things that did happen that were in your favor over number of trials or number of times you performed the experiment. But overall, the formula is just very similar between experimental probability and simple probability. That even if you were to get both of them confused, your math would still be correct. So, yeah, that's great. So we go ahead and spin, and we get these values. Let's say I get 2, 4, 4, 6, 4, 3, 4, 6, 3, 1, 6, 2, 2. Okay. So how many times did we spin it? We spin it 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12, and 13. So we spin it 13 times. So how many of these were favorable outcomes? We have 2, 4, 4 right here, another 4, 4, 2, and a 2. So let's go ahead and count these. We have 1, 2, 3, 4, 5, 6, and 7. So 7 favorable outcomes. So let's go ahead and plug this into our formula. So we have 7 over 13. And this cannot be simplified further because 13 is a prime number. We like 8 times 8 is equal to 4 times 2. So we could go ahead and simplify or even simplify down to 1. 13 can only be simplified down to 1 as a denominator. We can't divide 7 by 13, so the denominator will never reach 1. Excuse me. So what we saw here is 7 out of 13. If we go ahead and just simplify that, or like try to see that as a different value, plug that in. Let's try to see this as a percentage. We actually see that this is the same as, or very similar to, 53.8%. So in reality, in this one experiment, we saw that there was a 53.8% of getting what you wanted. But what we had seen with our simple probability, we saw that there was actually a 25% chance. So yes, what actually happens and what is your probability is probably not going to be the same. So let me write that in a different color. So simple probability is a theory of what might happen. That's why when people say that something happens like 1 out of a million possibilities, it could still happen. Like if you're walking outside and you might get struck by lightning, it might be a low possibility, but it's still a possibility. And you have the lovely thing with probability is that you try to reduce your risk, or you try to increase your favorable outcomes by changing things. So let's say that I wanted to get more favorable outcomes, I could get more numbers, and that would increase my favorable outcomes options, and I could overall increase the probability of it happening both in real life and also according to theory. Okay. So the probability can be expressed, as you can see, a fraction, a decimal, or a percent. All right, so now we're going to be getting into something else called dependent and independent probability. Okay, we are close to the halfway mark for class, so I'll go ahead and let everyone have a 10-minute break. And then once the timer goes off, we'll go ahead and come back from break. gonna be on break. Okay. Now we're going to talk about dependent and independent probability. And it's just like what the name entails. So here with dependent probability, the next occurrence depends on what happened. So let's go through a scenario. Dependent probability. Right? So you find the probability of So you find the probability of an event occurring, then find the probability of other events after it. Here's an example. So the best way that people describe this is by using diagrams or tree diagrams. You might also see this if you're into like computer programming or even into video games that come up with storylines that like if you do something like in one part of the video game, it like affects storyline later on. It's dependent. Same thing. So let's say that we're talking about again about a coin. Let's use a quarter. So let's say that there's two options. We're just gonna say that it can either land on heads or on tails. So it lands on heads. So quarter number one. And then we say quarter number two. Still quarter number one. Lands on tails. All right. So now from here, we get a second quarter. And then that one could be on heads or tails. Over here, again, we get a second quarter or flip it again, and then we'll get either again heads or tails. And then if we want to keep on going, we can either like more heads or tails. So this right here is actually a great segue into combinations of probability. So here we can have, all right, this possibility to land on head, head, and head, or possibility of it landing on head, head, tails, head, tails, head, head, tails, tails. You get the idea. So let's say, let's simplify this. Let's only make two instances. Let's say you want so if I want two quarters to land on heads, there's really only one combination that they can happen right here. So I look at it from these 4 overall possibilities. So it would be 1 out of 4 or a 25% chance. Now, let's say you want 1/4 on heads and another on tails without caring about the order. Okay, so heads and tails exist here. And tails is right here, so it's going to be tails and heads. So we have 2 out of 4. Same thing as 1/2, or as 0.5, or 50%. Ta-da! So here with this type of dependent probability, we're able to see that we can calculate based on one event and another event, and then we want to find out what is the overall probability. Another way that I could do this, if I don't want to go ahead and draw it out, I can even say that there is, let's see, let me make some space here. There is actually, and then if I want to look at all of this information together, I know that there is a possibility. Let me erase very carefully. Alright, let me just redraw it instead. So we have here heads, there we go. So let's say that I want to calculate the probability of it landing on heads again. So before I just basically said, well, it's going to be 1 out of 4 because I went ahead and circled and saw heads and heads happening only occurs 1 in 4 possibilities. And I did that very visually. But let's say that I don't have necessarily the time to go ahead and draw this tree out. I can just go ahead and multiply the probability of each instance together. So let me explain. We have 1.5 probability. So I say I want heads. So there's a 1.5, 1 out of 2 probability that will fall on heads, right? And then from heads, there's a 1 in 2 probability that will fall again on heads. So I can just multiply. So this is where knowing how to do your operations with fractions becomes very important. So if I just multiply straight across, I get 1 out of 4. So it's the same thing. It's 25% probability of a quarter landing on heads twice. There we go. That explains dependent probability. We use the first instance and we multiply it by following instance. Let's say it was wanting to talk about heads, would want heads to land 3 times in a row. I'd go ahead and just multiply by 1/2 yet again. In that case, I'd end up with 1 out of 8 possibility of that happening. So if there's no further questions, I'll move on to independent probability. So let me erase this. So with independent probability, it's just like what the word independent means. It doesn't need anyone else, or it doesn't depend on previous events. Each event is independent of each other. Oh, I am so sorry. The previous example was independent because I did each instance of the coin toss independently. It didn't depend on each other. We're going to talk about dependent right now. I'll go ahead and on the video, I'll go ahead and like add a little disclaimer that when I wrote it down, I didn't write the part that said in front of it saying not dependent. So we're going to talk about just dependent probability. So with dependent probability, each instance causes a change. So like let's say I have a little bag. And I've got like a bunch of little candies. Okay. So here I have a bag of candies, and I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I have 12 candies. And of those candies, I have 1, 2, 3, 4, 5 black candies. And I have 2, 3, 4, 5, 6, 7 white candies. There you go. So if I'm talking about the probability of me getting a black candy, it's going to be 5 out of 12. But let's say I eat the candy. That changes the total number of candies. So let's say I want to talk about what's the likelihood that I'll get, again, another black candy. Well, that changes things. Now, I have 4 black candies, because I ate one. There's still 7 white candies. And my total number of candies is also decreased to 11 candies. So the probability of getting the black candy changes to So if we go ahead and just convert this to percentage, I'm going to show you this interesting phenomenon. Go ahead and just type this in. Is very similar to .7%. Here, if I do 4/11, after just eating one candy, I have changed the probability. From 41.7% to 36.4%. That's why when people say that your luck's, like when you have like a winning streak, or that you've been very lucky sometimes, they will say your luck will run out. Not necessarily believing in luck, but your possibilities of having a favorable occurrence, which is getting the black candy, you'll eventually run out of black candies in the bag that you'll only be left with white candies. If this has ever happened to anyone who has eaten like cereal with marshmallows in it, and at some point you run out of marshmallows in the cereal, that whenever you try to get more cereal, you only get the actual corn flakes instead of the little squishy marshmallows you'd like. Same thing, you eventually start using them up. So here, let's do a mathematical calculation with this. So now we want to know, so we have, in the first time of getting a black candy, it's 5 out of 12. And then it becomes 4 out of 11 the second time. So let's say we want to know the probability of getting a black candy twice. We are going to have to change our values, because the actual total number of candies change as well as the black candies. We are going to have to multiply these two. Same thing as in the previous problem with independent probability. So this is where if you forget, or just like how I had done it previously, I had confused independent and dependent probability. You're still going to end up multiplying two different instances with each other, or two or more different instances with each other. The only thing with dependent, it depends on something. So the numerator and the denominator, one of them might change, okay? Or in this case, both the numerator and denominator change. So let me go ahead and just erase this. So I'm going to go ahead and just do this. So if I multiply straight across, I get the same thing as 20. And then 12 over times 11 is, just want to double check my math. Make sure I remember my multiplication tables from earlier years. Is 132. All right, I think I can go ahead and simplify this. No, actually, I can't. 11 is a prime number. But I can divide and simplify this into divided by 4. So if I want to go ahead and simplify, we're going to divide by 4 on the top and bottom. Ends up with 5, and I'm going to have 33. So the probability of getting the black candy twice is 5 out of 33. Any questions? Okay. Now we're going to move on into combinations. So with combinations, it wants to know all the different possibilities that you can mix something up together. And it becomes very important if you're just mixing one type of item or if you're mixing two different types of items. And I'll show an example to further explain. We'll first start with combinations with one type of item. So let's say Pete is making a salad. He wants to include 2 fruits in his salad. His options include apples, pears, bananas, grapes, apples, pears, bananas, grapes, and grapes. How many different combinations can he make? Something else I want to point out in this type of example, if I end up with a combination of apples and bananas, it's the same thing as putting bananas with apples. It doesn't matter in the grand scheme of things. I'm still going to end up with those 2 same fruits in the salad in a different combination, in a different order. But hence, that combination is going to be the same. So let's go ahead and write this out simply. So we have apples, and we have bananas, with grapes, and we have pears. And just to make it easier, we're going to use the first letter of each fruit for our combination purposes. There we go. So our options with apples are apple and banana, apple and grape, and here it says he wants to include 2 fruits. I want to make the distinction that he wants to include 2 different fruits. And then apple and pear. So here we have banana and apple, banana and grape, banana and pear. Here we have grape and apple, grape and banana, grape and pear. Here we have pear and apple, pear and banana, not peanut butter, and pear and grape. All right, so we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 12 combinations, but some of them might be repeats. These are repeats. These are repeats. And then the other repeat is this one. So truly we have 1, 2, 3, 4, 5, 6, 7, 8 different combinations. Oh no, actually no, these also go together. And these go together. So from this, we can tell that there's actually 6 different combinations. So that's one way we can do things, although it does get pretty messy. So here's another way we can go ahead and do that. We can go ahead and do a graph. I mean a different kind of visual representation. So let me go ahead and erase this. So from here, we were just able to put them together. Here we're going to say apples. Okay. So here, I'm going to put 2 things together on each line. So I'm going to put apples and bananas together. Then I can put apples and grapes together. Then I can put apples and pears together. Then going on to bananas, bananas with apples. I can put bananas with grapes. I can put bananas with pears. Moving on to the grapes, I can put grapes with apples, put grapes with bananas, and you put grapes with pears. Then finally I can put pears with apples, pears with bananas, pears with grapes, and there I have it. So if I go ahead and count these, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. But how many of these are duplicates? These are duplicates, these are duplicates, these are duplicates, these are duplicates, these and these. So if I count how many of those are different, again, I'm going to end up with 6 different combinations. Different way of writing it out, you can do whichever method that you like best. Okay, so now we're going to be doing a different kind of combination. We're going to be doing combinations with 2 types of items. You know, like, okay, how do we go about that? Here we're just talking about fruits. In our next example, we're going to be mixing different items together. So like whenever you're making a burger, what are different combinations you can make, or making an outfit, what are different pieces of clothing that you can put together. So let's get right into it. So let's do combinations with 2 or more than 1 type of item. So combinations with more than 1 type of item. So let's say that you are planning a trip. And want to find out the different outfit combinations that you could have. I want to know how many outfit combinations this is actually a very a good skill to have. That way you can actually, oh hey, look, if I only have these very few items, I can actually make like 20 different outfits. I don't need to pack as much clothing. I could even like make it easier to pack, and I won't have to wash as many different clothing. So you're planning a trip and you want to know how many outfit combinations you can have. You have 3 shirts. Two pairs of pants. And 1 pair of shoes. Something else I do want to point out, especially for our non-native English speakers, 2 pairs of pants doesn't mean 4 pants. We just call pants a pair of pants, usually because there's like 2 legs. So 1 set of pants is called a pair of pants because there's a pair of legs. So let's go ahead and write this out. Let's say we have shirt 1. We have shirt 2. And we have shirt 3. So we have our 3 different shirts. From there, we can pick out either pant 1 or pant 2. Same thing over here. Pant 1, pant 2. This is also the same thing, how people who are minimalists or people who have like a capsule wardrobe, this is the way that they're able to like determine if they need more clothing or make use of different combinations. That way it looks like they're wearing different things. And then since we can only wear 1 pair of shoes, well, it's the same pair of shoes. So we're just going to call it shoes. Again, we call this 1 pair because you have 2 feet. shoes. So what are the different combinations we have? We have 1, 2, 3, 4, 5, and 6 different combinations that we could wear. Great. So let's say we had actually 2 pairs of shoes. Let's make it more interesting. So you see it becomes a lot more complicated. The more combinations and then more types of items that you add on. There's actually a fun way we can deal with this. My handwriting just gets messier as I go down. So here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 different combinations. I actually prefer working with combinations of more than one type of item because each possible combination does not repeat itself. As in the previous one, there was the combinations actually doubled up because it was the same thing forwards and backwards. So that could just make it a little bit harder to keep track of things. This one is actually simpler. Excuse me. There's a shortcut though. I could just say, let's see what I have room. 3 shirts times 2 pairs of pants times 2 pairs of shoes. 2 times 2 is 6 times 2 is 12. Ha! I could have just done that and not had to draw out all of this. But now you can appreciate the beauty of combinations with more than one type of item. I could just multiply the different number of each type of item, and there I can get my total number of combinations. So let me go ahead and just say this. Easy way. Okay. So the next thing that we're going to go into are permutations, and then that would be it for the rest of the class. So let me go ahead and erase. So with permutations, we use them to find the number of possible outcomes where order does matter. In our previous example where we're talking about Pete wanting to make a salad, apples and bananas and apples, it was the same thing. Here with permutations, we want to find number of possible outcomes. where order does matter. So let's do an example. Let's say Kate is planning a vacation itinerary. Okay, so itinerary is just a fancy way of saying what's your plan or your schedule for a vacation. So she wants to, so let's say she wants to visit the art museum, try a new coffee shop, take photos, and take a walk. But not necessarily. Just want to double check I'm spelling the word necessarily correctly. Oh yes, it is one C and two S's. Necessarily. In that order. How many possible sequences are there? Okay, so we could say museum, coffee, photos. I meant to say she wants to take a walk. And then we can just keep on writing things in different orders. Because here it would make a big difference because all these 4 items are going to be included in the possibilities, but what she does first is very important. It's also very important when you're planning out your schedule. If you're planning on meeting up someone for coffee, maybe she says, well, I'm going to be at the museum for 2 hours. I gotta let them know that ahead of time. That way I can go meet someone for coffee. So here, order does matter. This is called a permutation. So we could go ahead and do what we've been doing before. We could do museum, coffee, photos, walk. Or do museum, photos, coffee, walk. Okay, we can do that, but it's going to be very long, very tedious, and it's very prone to error. So here we have a trick. We could just we know that there's 4 possibilities, right? And taking a bit of knowledge from our combinations with our dependent probability, like when we're taking the bag of candies and we're taking one candy out, it affects how many options are left. So here we're going to start off with 4. We're going to multiply that by 3 because there's 4 options, but if we do one of those options, we're only left with 3 other options. Same thing, we're going to multiply that by 2 because from those 3 options, we select 1, we're left with 2. And you guessed it, we're going to multiply that by 1 because we chose 1 from those options, we're left with 1. So we just multiply this, we are left with 24 possibilities. So 24 possible permutations. Much easier. So if you're just, if you're going across questions, you're not sure, okay, am I going to treat this like probability? Am I going to treat it as just multiplying, decreasing? You want to find out first, is it dependent? Is it independent? And then does order matter? That's going to affect how you're going to treat the problem. Okay? So let's do one more example. Okay. So let's say 10 friends are racing each other. They're trying to either win first, second, or third place. How many possible sequences? This is another key term. When you see the word sequence, big possibility, no pun intended, of it being a permutation. How many possible sequences of the top 3 winners are there? Okay, so I could go ahead and draw this out, and it would take a long time. I'd be very frustrated. Or I could just, knowing my rule for, okay, this is a type of dependent probability. So I'm starting off with 10 people, go down to 9, 8, 7. Oh, I'm sorry. I would go to this 7, 6, 5, 4, 3, 2, 1. If I was looking for all people organized from like first to 10th place, but the question only cares about the people who are first, second, and third place. So that's actually going to be less sequences that are available. So how do I do this? I go from top to bottom. I only care about first place, and then after one person wins first place, there's only 9 other people that are available for second place. And then after someone wins second place, there's only 8 more people that can win third place. That's why I go with 10, 9, 8. If I multiply 10 times 9, I get 900. Multiply that by 8. I'm sorry. This is 90. 10 times 9 is 90. Multiply that by 8, I get 720. Possible ways the runners can be arranged into first, second, and third place. Ta-da! Wow, permutations are just awesome. They make life so much more easy. Okay. So I'm actually seeing here that there is another section left in the data statistics and probability. I'm just going to go ahead and leave that for Monday. That way we can kind of just like review the chapter. It's going to be about comparing proportions in different formats. So then the quiz isn't going to include stuff that we haven't covered yet. I'll make a quiz on things from data, statistics, and probability, and then I'll make a second take-home quiz on ratio, proportion, and percent. So it's going to be like the first and second week, and I'll give you also hints on what section or what videos you want to reference to use the take-home quiz. That's all for tonight, and we'll see each other again on Monday. Have a good weekend.